Okay, now we're going to further develop our frequency distribution table. I've added a column here for proportion. There's our P for proportion. And remember, that's telling us what fraction or what part of each score is it associated with the total score. I didn't say that very well, did I? What part of the data, what part of the total data is associated with each score? That's the word I keep missing. What part of the total data, what fraction of the total data is associated with each particular score? So to calculate this is pretty straightforward. A proportion says, well, figure out what the frequency of that score is and divide it by the number of those scores. I started this example as a population, so I'm writing a capital N there. If I had started this example saying it was a sample, I'd write a lowercase n there. Again, mathematically, it makes no difference. The only difference is telling us the data came from a population or a sample. But relative to the calculator doesn't care where the data came from. So all we're going to do here is simply plug in. So I want to know what proportion of my data, of my total data, what proportion of my data is associated with the raw score of 5? Well, I need to know how many 5s there are. There's 1 5. And I have to divide that by the total number of scores. Well, we know from working it before that the total number of scores is 14. So it's 1 out of 14. Now again, the textbook definition says fraction, but we don't work in fractions, we work in decimals. So we're simply going to divide it. So 1 divided by 14. And what we see is a long, infinite, non-repeating decimal. So, what to do? This is very important because this is a rule that's going to be with us all semester long. We need consistency. There's more than one way to round numbers. There are several different rounding systems out there. We're going to go with the most common and easiest, the one that pretty much everybody already knows. But we need to be consistent about it. So, if your answer contains a decimal, like this does, there's a decimal, it's not a whole number. If your answer contains a decimal, it must be reported rounded to 2 places, to the hundredths place. So what this says is we're going to go over to the second place, and we're only going to write it 2 digits long. Most of you already know, to figure out exactly what to do, we look at the third digit. If it's if it's 5 or higher, we round the preceding digit up. So if this was 0.077, that third digit is higher than 5, so it becomes 0.08. If it's 4 or less, you leave it alone. So in this case, a 1 is 4 or less, so what we're going to write is, the answer is 0.07. Now this leading 0, you don't have to put it there. If you're going to do it on one answer, do it on all of them. It's about consistency. So if I put it there, it needs to be on all of them in this table. We don't sometimes put it and sometimes not. It confuses the reader. They don't know what that means, why it's so inconsistent. So again, if your answer contains a decimal, you always report it rounded to 2 places with proper common rounding. That's always the case. So now I want to know what proportion of my data is associated with the raw score of 4. Well, there are 3 4s, so the frequency is 3. The number of scores is still 14. So 3 divided by 14. And we're going to have to round again. And when we do, we're going to get the answer of, where am I? 0.21. What proportion of my data is associated with a raw score of 3? Well, that's 5 out of 14, so 5 divided by 14. And again, we report that rounded. Oh, let me fix that because that's not actually true. That was from the previous example. We actually had, 3 2s is what the original data was. If that was still a 0, that wouldn't be a 14 anymore, and all this would be wrong. Yeah, I forgot to change that back. Sorry about that. What proportion of the total data is associated with a score of 2? Well, again, there's 3 of them. 3 out of 14 is, again, 0.21. 3 out of 14, 3 out of 14. Same proportions on either one. And lastly, what proportion of my data is associated with raw scores of a 2? And that is 0.14. Now, I've said before, and so I'm saying again now, and I will say over and over as the semester unwinds, as I promised you, if you can double check your work, you should double check your work. So in this case, the way we can double check this is we have one whole set of data that we've broken down into little parts. 0.07, 0.21, 0.36, 0.21, 0.14. If we put all those pieces back together, it should equal one whole set of data again. So add 0.07 plus 0.21 plus 0.36, 0.21, 0.14, add up this column, and if we've done everything correctly, it should turn out to be 1. Except it doesn't turn out to be 1 in this case. Why not? Because of all this rounding we had to do. We had to take some of the value and throw it away, so we're a little bit short. So it actually comes out to 0.99, which means we've done it correctly. If we've had to do some rounding, it might turn out to be 1, but it might also turn out to be 0.99. On really rare, weird data, it might be 1.01, but it should only be off by 100th, 0.99. If you add all this up and you get 0.95, you've got a mistake in there. That's not rounding. There's a math mistake somewhere in there. If there had been no rounding at all, if it just had all worked out as whole numbers or just perfectly perfect numbers that didn't need any rounding, this should add up to exactly 1. And if it doesn't, then you know you've got a mistake in there. So that's our column for proportion. We're going to add one more column onto this table for our last column here. Oops, not frequency again, sorry. Percentage. Now, in truth, in the real world, you would never build a frequency distribution table that had both of these columns, and because it's the same information. It's a communication tool, right? I keep saying that. So who am I trying to communicate with? If I'm talking to other scientists, I'm probably going to use the proportion table. But everyday people don't really think in proportion terms. We think in percentage terms. So to get our percentage, we simply take the proportion and multiply it by 100. So essentially, we're just going to kick the decimal place over 2 spots. So 0.07 times 100 becomes 7%, 21%, 36%, 21%, and again 14%. All we got to do is kick that decimal place over twice, but you can double check those. Now again, if you can double check your work, you should. So it would be the same thing here. If we took 100% of the data and divided it into these little piles, put all the piles back together, it should be 100% of the data again. And just like the preceding column, it's going to add up to 99% because of the rounding errors. But because we know we've rounded in our data, we would know that that's probably fine, that we probably did it right. Again, if we added this up and got 97% or added this up and got 106%, that's not rounding errors, that's math error. You miscounted something or miscalculated something. So this is a completed frequency distribution table that includes columns for both proportion and percent. You should make sure that you know how to build these. When you're doing these for ourselves online, you'll be building these tables using the table tool inside of Canvas. So you'll see it right above the field where you're writing. There's a table. So if you were going to build this table, you'd know you'd need 1, 2, 3, 4 columns and 1, 2, 3, 4, 5, 6 rows. And then they would drop the table in there for you and you just type your answers in. So that is a frequency distribution table, kind of the basic version of it. So we're going to advance this topic another step in the next video, talking about what are called grouped frequency distribution tables. We'll see you there.